Cool. So I'm Kyle Pointer, and I read this paper that I think is pretty cool. You might say I love it. That might be a very strong word for it. But I enjoyed reading it. It's called On Certain Formal Properties of Grammars, and it was published in, I think, 1959 by Noam Chomsky, who is apparently a linguist or something. I don't know. That's, I think, the case. Yeah, it was published in, I think it's the Journal of Information and Control. And there was another paper that was very similar that was published a couple years beforehand that was called 3 Models for the Description of Language, and a lot of the subject matter is very similar. And in fact, the paper that I read, the On Certain Formal Properties of Grammars, is almost a little bit of a rehashing of the first one, it seems. But this one is typeset really nicely, and it's legible. Whereas the other one looks like it was on a typewriter, and the math also looks like it was on a typewriter, which really sucks. So I read this one, which I found because I've been reading this cool book called Understanding Computation. I think it was written by a Tom Stewart. It's published by O'Reilly. There's some sort of mollusk on the front of it because it's an O'Reilly book. And so that book had a couple chapters on various kinds of automata, and that got me really interested in what they're capable of dealing with, and then ways that they can be classified. And I started reading about formal languages and formal grammars, and then I found this paper as a footnote on a Wikipedia article, which is how I learn everything. So I think that the impetus for this is that is this idea that a theory of languages or a language would contain some way of classifying the certain grammars that can sort of define them. And this paper has a fairly particular sort of definition for grammar and language that are very sort of formal. And they are pretty much that a language is a collection of sentences of finite length, all constructed from a finite alphabet of symbols. So it's not necessarily going to be a natural language that's being referred to. It could be a language that contains a sentence like, Tom bit the dog, or it can be a language with sentences like A, B, B, C, D, 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 A, B, Q. Those are both options. Another language would be, which is the language that is also an empty set. That was funny. I actually don't know if that can be, it doesn't matter. And then in this paper, a grammar is, what is meant by a grammar in this paper is a device that enumerates the sentences of a language. So if we can pretend that there's these little machines that sit around and pop out little sentences all the time, they can be this very abstract thing. Or they can be little state machines, they can be Turing machines, they can be anything in between. And a big part of that is actually sort of the point of this paper, is that different grammars are sort of equivalent in their generative power, which is their ability to create all the sentences of a language. Different grammars are equivalent to different sorts of machines in what they can generate. So if you have a regular grammar, then you can use a state machine to generate or recognize all of its sentences. And there's more on that later, because that's my favorite part. So in order to discuss these sorts of grammars and these sorts of machines in a really abstract way, there's this device that is a phrase structure grammar, which is really just a set of rules for rewriting parts of sentences. And they sort of move from a most abstract possible sentence and into a completely concrete sentence. And there will be more on that too. There's like a really particular formal definition for how these work. And one sentence that I think is a real doozy is that G is a semigroup under concatenation with strings and a finite set V of symbols as its elements and I as the identity element, which is really fun. I have no idea what it means. But really what it means, I think, is that whenever you're talking about these strings, for them to be a semigroup, I'm pretty sure it just means that you have to be able to add them together associatively. Just like if you have like A plus B in parentheses plus C, and you know how that's equal to A plus parentheses B plus C, concatenating strings works in the same way, which is really easy to tell on this imaginary whiteboard that's to the right of this screen. And a grammar like this is going to have a set of symbols that are its vocabulary. So this can be like, I guess if you're talking about like a programming language, these can sort of be tokens. Or they can just be like letters, words, sort of what have you. But some of them are terminal, and some of them are non-terminal. And it has to be one or the other. And we'll talk about those in a second. And then there's this idea of a boundary element, which is sort of the beginning and end of the string. Like you can't have one in the middle, it doesn't make any sense. And I think that for the most part, the point of having the boundary element is like a bit of a convenience for writing things down. So you know if you're actually talking about the beginning and end of something, or if you just have some like some ambiguous term like in a string. There'll be examples.
Strictly speaking, and since Deech isn't here, I'll toss this in for him. It's actually a monoid because it's semigroup with an identity element.
So, ooh, that's exciting.
So
I love monoids.
More category.
And then there's some axiom on this like production rule, or this arrow, which is usually read as can be rewritten as. So there'll be an actual example here in a second, but if anyone else can take a better stab at this than I can, you're welcome to. But it's irreflexive because I don't think it makes sense to say that something is rewritten as itself, and I think that might be a reason why that's sort of a rule that's articulated. And then it's an element is an element of the non-terminal vocabulary if and only if there exists a rule that takes that non-terminal, that takes that symbol and turns it into something else. And then there's no rule that sticks like the boundary symbol like in the middle of a string, because that doesn't make sense. And then the last thing is totally beyond me, but he like writes afterwards that it just means that there's sort of a finite set of rewriting rules, which is exciting.
I'm having a little trouble with omega. I'm not entirely sure what.
With which one?
With omega. I'm not sure what the conditions are on omega.
Oh,
I'll
there's some more clear ones.
Okay.
And this is just an example of one such grammar. Oh, and I think I forgot to mention, the non-terminal vocabulary is going to contain an element S, which is sort of the the longest string, but I think of it as like the most abstract possible like sentence you can have. And like from this, there will be rules that sort of take it and rewrite it as something more concrete. So one example, the one that's actually in the paper, is this set of 4 rules, which just say that S can be rewritten as AB, A can be rewritten as C, CB can be rewritten as CB, which I guess is maybe a little bit confusing, but keep in mind that if the symbol is uppercase, then it's that's supposed to indicate that it's non-terminal, and that it can be written as something else. It's just sort of a what would you call it? It's a convention whenever writing these rules. Whereas the lowercase b and the lowercase a would represent terminal symbols. So they would be like the concrete idea, sort of. And then so what you can do is you have that short, it doesn't have to be short, it has to be finite. You have that list of rules, and you can go from S, which is your starting, or the longest string, as it were, and you know that you can rewrite that as AB, and then there's other rules that say that you can rewrite AB as CB by applying one of those other rewriting rules. You can rewrite CB as C lowercase b, applying another rule, and eventually you can end up with AB. This is the notation that he uses in the paper, but I like writing it like this. And it is called a derivation of a phrase structure grammar whenever you start in one place, apply the rewriting rules, and then end in another place. So this could be written as just like S, fat arrow, AB, but usually if there's more than one step happening, there'll be like a little star, a little plus next to the arrow. And then you can also sort of represent it as a tree, which in this really abstract case is just sort of weird, but you can also think of it as like, if we take S to be a sentence, and then A to be a noun phrase, C to be like a singular noun, and then we can, as we move from the abstract to the concrete, we eventually can end up with a sentence like John comes, which is the example in the paper. So the thing that I think is really cool is that you can start getting languages that are just, qualitatively different by changing how the rewriting rules have to look. If you don't have any of these restrictions, the language is a type 0 language, and the grammar is referred to as a type 0 grammar. But as you add more rules, you start to get different languages that look different. But what I think is really interesting is that as you add rules, the amount of power you need, like in a computer, to actually generate or sort of recognize the language sort of decreases, which that sort of makes sense. But I think it's really exciting. So the first sort of restriction that they think to put is that in this rewriting rule, if phi can be rewritten as psi, then there are a, phi 1, phi 2, omega, such that phi is equal to phi 1, a, phi 2, and omega is not the identity element, or the empty, the empty string. And this rule doesn't really tell us that much, except that you can't take something and rewrite it as nothing, if I understand it correctly. And then another restriction you can put on them is that first restriction plus an additional restriction, which is but A arrow omega. And the sort of important thing, I think, in this restriction is to see that whenever there's just the A written here, this is supposed to, if I read the paper right, this is supposed to imply that there is no extra context around that A. So the left-hand side has to be just a single non-terminal symbol. And the right-hand side can be whatever you want, except for an empty string. And then the third restriction, which is my favorite restriction, is the same thing as the last two, plus this additional stipulation that omega be a non-terminal symbol followed by, a terminal symbol followed by a non-terminal symbol, or a single terminal symbol. And this one's really cool because this is sort of what, because of this restriction, you get sort of a definition of a type of language that is really, really easy to turn into a state machine, which I find very exciting.
Yeah, and the significance there is that if you didn't have that restriction, then you could create a language that had a whole bunch of operations that were all nothing, and then you have an infinite number of possibilities for anything at all. It really makes the whole thing fall apart.
Yeah, it starts to be, I think that computing things becomes difficult whenever there's like a million things that cannot happen and you have to consider all of them. But I mean, this is all very new to me. I never took a course on this. I studied German. So, yeah, and I sort of said this already, but the idea of a type like I language, where I got, this is a quote from the paper, but if it's a type 1 language, it has restriction 1 like applied to each of its rewriting rules. Each of its production rules is another thing that they get referred to as. And then like type 3, restriction 3 is applied to each of them. And it must be applied to each of them. It has to be all of them have to meet that criteria. So the thing that I think is really cool that comes out of this is this definition of a hierarchy of sort of languages and grammars that at the same time represents the computational power and theory of different kinds of machines. In the paper, he doesn't use a lot of the machine types that I list on the right, because I don't think people used those words at the time. Like instead of finite state automaton, he uses this idea of like a Markov source, which we can talk about in a minute, because it's exciting. But the thing that I think is really cool is that if you don't have any of these restrictions on the rules and the grammar, then you have this like, you have a Turing machine, basically. You can have a grammar that has the same generative power as a computer that can compute like anything. If I understand what a Turing machine is, that's kind of what I understand it to be. Correct me if I'm wrong, I don't actually know.
Anything that's computed.
But very, very powerful, right?
Yeah.
Like,
Yeah.
I feel like that's a fair statement.
But it can't compute anything. That's actually probably the case.
Ah, well then that's not true.
But it can compute anything that is computable.
computable.
Yeah, it's incredibly powerful. Yeah.
Oh. Okay, yeah, that makes sense. If it can be computed, then this can compute it. Is that fair? Okay. These are new to me. And then this linear bounded automaton, I think, is like a Turing machine with some restrictions on it. I'm not sure what those are. eventually I'll figure that out too. Well,
Oh.
I'm really glad it turned right back on. Usually it doesn't. And then, yeah, so as you put these restrictions on, you start to get less and less powerful machines that are required to sort of generate or recognize this language, which I think is very exciting. And my absolute favorite part of the paper is this Theorem 6, which, you know, I mean, this is old news to a lot of people. It was probably old news in 1959 when this was published, but there's a type 3 language is a language that can be generated by a state machine, where like no stack, no memory, just your current state and a function that tells you where to go on what input. Although of course in this case he wasn't talking about a state he wasn't talking about a recognizer. He was talking about a generator. I'm still not totally clear on like whether or not they are sort of technically the same thing, but the one he talks about is this Markov source, which I thought was really cool, and I'll define wrong, but in a way that is convenient for me. And I say that they're just state machines that move between their states, emitting a symbol on each transition. More or less, you can define them in a very formal way, I guess, by saying they're a tuple with a set and a function and some other stuff. Although it might be a relation and not a function. It's one of those. I don't really know. Good enough? Good. And then it's not really a proof per se, although it's listed as one. I think it might be sort of debatable whether or not this constitutes a proof. But if we suppose that G is a type 3 grammar, then we know that all of its rewriting rules look like this or like this. And because of how like simplified that makes everything, it's fairly easy to take this sort of a grammar and then like construct a state machine that will, or in this case, we can make a Markov source that will generate that all of the, like theoretically, all of the sentences of that language. So I guess if you have, I might switch to the board kind of. But I guess that like, if you just happen to have a machine that looked like this, if this were like the world's simplest like Markov source that's missing a couple things, then if you move from one state to another, then you will like emit something during that transition. And in this paper, I guess the idea is that a lot of your sentences will sort of look like you have this boundary character, and then you have like whatever, and then you have another boundary character. So you can have the boundary symbol followed by any number of symbols depending on what all of the rewriting rules are, and then you have another boundary symbol. And the way he decides to interpret it is sort of that, actually I've got an example that I tried to write earlier. Hope I have one that actually makes sense. Is that whenever this goes from like, if you have a starting state, and it goes from the starting state into the first state, which is going to be your S in your grammar, then during that what do you call that? During that transition, it emits this boundary character. So it'll start emitting your sentence. And then once you end up in a final state, it like resets itself and emits the one at the end. And in this way, we can have whatever rules in the middle we want, and then we can generate the sentence, or any number of sentences. And the example I came up with, which is probably wrong because I came up with it, and I'm probably going to draw it really bad, but it's a grammar that looks like this. And in the rules I talked about earlier, you just sort of write every single rule. If you have the little bar here, it just means that C arrow CS or C arrow D. So it saves me writing something, and then I get to explain it. So this is a fun one. This is a cool little mark. Well, it's probably not really a Markov source. I'm using a really wishy-washy definition here. I'm just thinking of like an inverted state machine that's like emitting things instead of accepting things. But you could have this, and we could sort of draw it to look like this, and hopefully I did it right, because I'm completely unable to critically think while I'm at a whiteboard. Is that an A? Oh, it's an S. Yes, that's right. Perfect. Okay. And this is going to be super ugly because I don't know how to draw things. They're always really pretty in books. So, there's one more, which is the final state. And whenever he's talking about interpreting these grammars as state machines, a rule that looks like this can sort of be interpreted in here as you're going from some state where this is the non-terminal symbol, or in this case, this is the non-terminal symbol from which you're moving, and then this other non-terminal symbol is the one that you're moving to, and that this letter right here is the symbol that gets emitted by the Markov source during that transition. So we can take these rules and we can draw little arrows in this diagram. So we know there's this initial state, and we go to the start, and that emits that little hash. I tried to call it a dollar sign, but it's a hash, it's a sharp, it's an octothorpe. It's actually called an octothorpe. So we got that one, and then we see that S arrow AB, so we know we can get from S to B, and in doing so we can emit an A. And then we have B arrow BC, so we know we can get from B to C, and in doing so we emit a B. And these could be like any number of things. They don't have to be A's and B's. They could be Z's and Q's and P's and M's. But it was convenient to use these letters. And then we got another rule that says if we're at C, we can go to S and emit a C on our way there.
C.
Did I do
You
something?
wrote an A instead of a C on your
That's
image.
hard. Thank you. I would have been very confused whenever the regular expression that this is supposed to look like didn't work. And I would have cried. I would have broken down in front of everyone. a C, which is different than an A. That is really good though, because now I seriously would have freaked out. And then there's one more rule that says C can go to D. I don't know where D is. Oh, it can go to the final state, that's what it is. And it emits a D along the way, during that transition, as it were. And I think for this to technically be a Markov source, there have to be like probabilities that dictate like if you're in any one place, like what the whether you should end up here or here. And it's I don't know that, but this works good enough for me. And then of course once you're here, the machine sort of like resets so it can generate another sentence because that's what it likes to do. And it goes back to the initial state so it can generate more sentences. And that sort of caps the sentence with the other, I don't know what to call it, I just talked about it, the end of word symbol, end of sentence symbol.
Boundary.
What?
Boundary.
What?
Yeah.
Yeah. So this one's cool, and unless I made a mistake, I'm pretty sure, oh yeah, let me talk about my favorite thing with type 3 grammars, is that they're sort of, the languages they generate are regular languages. In the paper, there's another definition for regular languages, which I'm ignoring, because it's not as convenient for me to talk about, which is different than the one I'm about to talk about. So if that's confusing, it's confusing. So the cool thing about type 3 languages is that they are, I mean, one, you can represent them with state machines, which is really exciting. And the other thing is that there are things that can be recognized by a regular expression matcher on your computer. And in fact, you can implement something that will check whether or not a string matches a regular expression. And you can do it with little state machines. You have to figure out a good way to make it happen on your computer, but it works. I did it once, and it worked for at least 2 regular expressions. They're very short, because once you start concatenating them together, it's not like super hard, but it starts to get a little bit more complicated. So yeah, that's cool. So as like the example of what this one can do, so you start out, you move to S, and since you move to S, this is our sentence. I can't spell sentence, so I'm just going to draw an arrow. You emit this little symbol that says, oh look, I'm starting a sentence. And then, once you're at S, what can you do? Oh, the only thing you can do in this state machine, although it could be different if these rules were different, is move to B. And whenever you move to B, you emit an A. And then you're at B, you can move to C, so you emit a B. And then, what's that? You're at C, and you can move to S, so you emit a C. And you can keep doing it. In fact, you can keep doing it as many times as you want. Let's do it one more time. I'm actually going to get really confused because moving my finger is not actually helping. So we've emitted a B, and then you can either go back to S, or you can go to the final state and emit a D. And then once you're there, you go back to the start, and you emit that little pound thingy, the end beginning of sentence symbol. Now, you can keep doing this part over and over again, and you can eventually break out whenever you want. But this is my example that I think is cool because, unless I'm wrong, and it would really suck if I'm wrong at this point after all this build-up, but this is pretty much equivalent to the regular expression you might use that looks like this. And just for good measure, actually, we'll do the caret and the dollar sign. Well, no, that doesn't
Yeah,
actually
no,
make any
no.
sense in this context. But yeah,
Yes,
Oh.
this isn't quite it because you can have ABD.
Yeah, well, you
Can
have
I?
to have ABD. ABD is how you terminate.
Oh. Well, there's another regular expression.
Yeah.
Yeah, there is
Yeah,
a
there's
regular
like-
expression that will do this.
Yeah.
Yeah. So my example is bad.
Yeah, it's close.
It's good.
How would we fix that? ABD. Oh,
I wouldn't get hung up on it. I've been staring
Yeah.
at it for a while.
yeah, it's probably not worth it. But yeah, so my example is wrong, but
The point is,
the fact that you can do it and all you need is like this little list of rules, and then like computers use this all the time, that's really exciting to me. And that's my favorite thing out of this paper. Yeah, so are there any questions that are really easy?
So, do you have any questions at this point? I'm just gonna comment, I felt bad because I didn't get a chance to read the paper before I came here. I said, I really ought to read the paper. Now I actually have to read the paper, because this ties together a whole bunch of things that I didn't really quite connect, that I've learned in various places. So
Yeah.
now I need to actually go read this paper.
Yeah, I need to finish it because there are definitely pieces where I'm like, oh, that and that. Like, now I understand the bridge between
Yeah.
these things that I had not connected previously.
Yeah.
Yeah. I just think it's really cool that there's like, talking about languages, you're trying to sort of come up with a way to sort of categorize and discuss what can happen in a natural language. Then all of a sudden, computers, like, they just like happened. And I'm sure it's in no way a coincidence. And in fact, I'm pretty sure that in the paper there's a couple times where he's like, this isn't that useful for natural languages. Like,
Yeah.
it's kind of like round hole square peg, however that's said. I don't know, but there can be difficulties there.
Chomsky's kind of funny because I feel like there were quite a few times where he just kind of dumped on, like, this category of languages where he's like, yeah, there are all these really interesting languages in terms of contextual grammar, like this stuff that people are using to speak, and then there's this other stuff that they're looking at for computation that I don't really like. It's not very interesting, but he kept doing stuff in it, and I don't know what, like.
Honestly, there's so much built between regular expressions and the next step up to context-free grammars.
Yeah.
You've got so much you can do with those two things.
Yeah.
It's real interesting.
And there's a
So I
couple,
like the formalism here, that there's a way to kind of enumerate what are the differences on this.
Yeah.
I wish I were better at formalisms, but someday I'll take computer science courses. He does have a couple really great little things in here, but I'm not going to be able to find while I'm standing here. Let's see. Yeah. The weakest condition that can significantly be placed on grammars is that F be included in the class of general, unrestricted Turing machines. The strongest, most limiting condition that has been suggested is that each grammar be a finite Markovian source, or a finite automaton. The latter condition is known to be too strong. If F is limited in this way, it will not contain a grammar for English. The former condition, on the other hand, has no interest. We learn nothing about a natural language from the fact that its sentences can be effectively displayed. Well, he's right. But, I think he's right. I trust him. But, yeah. So I guess, like, getting to make interesting claims about natural languages somewhere between those two extremely different, like, kinds of computers, which is all very fun. But there's a lot of there's a lot of room to play in there, so I like that. Yeah.
Very nice.
That's all I have to say.
Yay.